Not 6:30. Okay. So here's a couple options. Do you let these people walk on your back?
The ballerina.
The ballerina. Maybe.
Ballerina, not the other one. Depends on what you're into.
What are those? Oh, as long as she's not on point.
What physics question should you ask about though? If someone's gonna step on you, what do you care about?
Pressure.
Pressure. The like
It's
surface
pressure, but what is
area
pressure
of
made
the-
up of?
What's the weight?
Their weight. You want to know what they weigh, right?
And the area. What contact area?
And the cross-sectional area of the contact point, okay? So
Okay.
that gives you pressure. Force over area gives you pressure. So even if this little girl puts on these shoes and steps on you, it's gonna hurt more. She hasn't changed weight, but the surface area that's in contact with you is going to change, okay? So pressure is a valuable tool for understanding things because it's more than just force. It tells you how the force is distributed, all right? This is actually, somebody told me this is the wrong gauge, so we're gonna pretend that didn't happen. Pressure, I realized that like my understanding of a lot of the world is very theoretical. So like I had to install my own dishwasher and I was like, I technically know how household electrical systems work and I have a multimeter and I figured it out, but there is some knowledge that's very specific to just knowing how to do stuff that helps. So
Same with cars.
And I didn't even blow anything up, so it was great. Yeah, yeah. Same with cars. Yeah, cars, households, plumbing.
Cars are way easier.
Yeah, but I have a working dishwasher, so apparently theoretical knowledge is almost as good as functional knowledge. Yeah, I got really mad at Home Depot because they can't schedule an appointment. All right, so pressure is equal to force over area. If you want to write that in symbols, that is F over A equals P. All right, and we overuse the letter P. It's everywhere. Not to be confused with
Row.
Yeah, be careful how you write your P's and rows. Mind your P's and other P's, okay? Yes, it's a joke. The jokes, they're coming. Okay, units of pressure that we use in physics. Pascals, which is a Newton per meter squared because force over area. There are other units of pressure that other people use. Any atmospheres? Chemistry likes atmospheres.
Milligrams.
There's millimeters of mercury.
That's what it
Yeah.
is.
We will actually, we'll have a better understanding of why you would use that unit. It's a very practical unit from like physical experience of actually using things like thermometers to measure pressure. But yeah, other than that, it sounds fucking dumb.
Truly.
It's not though. It has a significance. Okay, yeah. Liquids, they exert pressure on the container because of gravity. Gases, the way they exert pressure is a little bit different. That has to do with the energy of the molecules. So gases exert pressure on a container by like bouncing molecules off the container. Liquids do it by having gravity push this incompressible fluid out and down. Well, mostly down and then slightly. Okay, so here we want to know which thing exerts more pressure. So we want to highlight the idea that we're looking at pressure. So pressure, and our definition of pressure is equal to force over area. So that's what we're looking at here. We want to know if an elephant is a very bad elephant. Oops. An elephant or a woman standing in high heels. It's not going to be an even worse woman. Exerts more pressure. So the point here is we have these points of interest. So this is where things are in contact with the ground, okay? So the first thing to remember is
how many feet does an elephant have, right? So the elephant has 4 feet, and most women have 2 feet, a few exceptions. So we know the mass of both the elephant and the woman, and we know the radius of the feet, and we're just going to assume for the sake of this problem that the feet heels are circles. So, this would be elephant foot, and it has a radius of 20 centimeters, and then we'll have the heel which will also now have a radius of 5 millimeters. So circles, that's an assumption that we're making. We also assume that elephants have 4 feet and women have 2. So in order to consider the pressure, right, we need both force and we need area. So let's start with the elephant. So the force, how do we get force? Well, for the force of the elephant, that's going to be mg, right, with the mass of the elephant. So that's going to be 4,000 kilograms times 9.8 meters per second squared. And that's going to give us 39,200 newtons. Okay? The area of an elephant foot is the area of a circle times 4. So 4 times pi r squared. Remember, that's the area of a circle. Oh, why did it do that? 4 times pi r squared. Okay? And we can calculate that out. 4 times pi, and the radius is going to be 0.2 meters, and we're going to square that. So that's going to give us an area of 0.5264 meters squared. Okay, so for our elephant, we get a pressure for the elephant of force divided by area, so 39,200 newtons divided by 0.5264 meters squared, and that's going to be 7.8 times 10 to the 4th pascals. All right, and this is our first part of our answer. So we'll start with highlighting that. So this is the elephant. We'll make this elephant purple so we can tell what we're dealing with. All right. And then we'll move on to woman with heels. All right, and we're going to follow the same process. We'll start with the force of the heels, and that's going to be the mass of the woman times g. So that's 60 kilograms, 9.8 meters per second squared. That's going to give us about 588 newtons. So as we would expect, right, the weight of the woman and the weight of the elephant are pretty drastically different. The women weigh less than elephants for the most part. And then the area is now the area of the heel. Remember, women have 2 feet in this case, and times pi r squared. That's the area of the circle. We're going to use the radius of the heel this time. So that's 2 times pi 0.005 meters squared, okay, because that's 5 millimeters. And so the area of the heel is going to be, well, of the two heels, is going to be 1.57 times 10 to the negative 4 meters squared. So that's pretty small. You can see this is much smaller than this. And so once again, we're going to find the pressure of the heel, and that's going to be force of the woman over area of the heel. So that's 588 newtons divided by 1.57 times 10 to the negative 4 meters squared. And that's going to give us 3.74 times 10 to the 6th pascals. So here is our woman in heels. This is our pressure. Now we just have to decide which one of these is bigger. Well, 10 to the 6th, usually bigger than 10 to the 4th. So this means that the larger amount of pressure is exerted by the heels. So getting stepped on by a stiletto is more painful and more horrifying because there's more pressure than being stepped on by an elephant, just for reference, in case you need to know that. All right.
So, what's a fluid, liquids, and gases? We are currently immersed in a fluid. What is that fluid?
Air.
Yeah, air. Some oxygen, nitrogen, some other stuff. Methane sometimes. So, if you want to sort of take a picture of this, let's say this is space, this is Earth. The way our atmosphere is, it's attracted to the Earth, okay? Which means as you get closer to Earth, the atmosphere gets more dense, meaning air gets more dense, okay? So here's, if you want to think about this as a giant cylinder, which is, I don't know why you would want to do that, but just for the picture, okay? This would be the walls of an imaginary cylinder. You can see up here, less dense, down here, more dense. And part of this is because each layer of air is pressing down on all the layers below it, okay? Have you ever dove down in water? What happens as you go deeper in water?
Big pressure.
Yeah, your ears hurt, and that's because the pressure is increasing, okay? So as you go deeper in any fluid, you're going to get more and more pressure, well, if you're on Earth, okay? Because gravity is pushing down. So it's sort of like if you stack books on top of each other, the most force is going to be on the bottom book, okay? But think of that with a fluid, which is a little bit trickier. All right, here's a fun video. We're gonna take a video break. I'm gonna add sound because this guy's Australian, so you should definitely hear him.
Hell yeah.
Today I'm at the University of Sydney with Dr. Phil, and we're talking about the pressure that all of us are under.
You are under a lot of pressure, probably 10,000 kilograms.
10,000 kilograms is pressing in on my whole body.
All from all sides.
Where does all this pressure come from?
It's from the air.
That looks like a dance move. Is that what you pull out on the dance
I'm
floor?
lifting 10,000 kilograms
You're
of air.
lifting the air. How much air is there above us?
About 20 kilometers or so. So you're at the bottom of an ocean of air.
So essentially the weight of the air is squishing me in.
That's right.
And all of us, you too.
And me too.
Wow. You seem to be holding up rather well, though.
Thank you, thank you.
How do you do it? What is
Well,
your
I've
secret?
got this special trick.
Uh-huh.
I've got the same amount of pressure inside me.
Okay. So since the pressure is equal inside and outside of you, you're in equilibrium and there's no sort of crushing or expansion.
No, that's right.
Okay.
That's right.
Well, most people, I think, don't recognize the pressure that they're under.
Yeah.
At least due to the atmosphere.
That's right.
How can we demonstrate that the atmosphere is exerting this huge pressure on everyone?
The best thing to do is to scoop out their insides, and then there'll be no pressure on the inside, and then they'll be
crushed by the atmosphere.
by the atmosphere.
And that will be a rather clear demonstration
Exactly.
of the power of the atmosphere.
Exactly.
But let's say we didn't want to kill anyone. How can we demonstrate this in, say, a lab?
Well, we could take a model of a person.
And this drum is meant to be a model of a person.
That's correct. Yeah.
Okay. And so what are we going to do with it?
So what we're going to do
Yeah, go ahead.
is we're going to put some water in here.
Why don't we go ahead and do it?
Okay, let's do it. Get it heating up.
So we've got some water in the drum, and we're heating it up on this little gas stove here.
That's right.
Okay. And what is that doing for us?
So the water will heat up and begin to boil. So it'll turn from liquid into a vapor. That vapor will push out some of the air.
Okay, so basically we're going to remove the air from inside the drum and replace it with water vapor?
That's right.
Okay.
Okay, then once we're sure that it's pretty much emptied of air, we put the stopper in and cool it back down again.
Okay, so that's going to condense the water vapor.
That's right.
And so what does that do to the pressure inside the drum?
It'll become much smaller.
Okay, and then we're going to be able to see what the atmosphere does when there's no pressure on the inside to
Pushing
push
out.
out. Excellent.
Exactly.
All right, well, I'll look forward to that.
All right.
So how long do we have to wait for this to boil and get all sorted?
Couple of minutes.
Should we do a little time-lapse effect?
Let's do that.
All right.
Okay, looks like we're boiling away furiously here,
All
which
right.
is pretty good. So it's about time to perform the experiment.
Let's do it.
But it might be a bit dramatic, so I'm going to chuck on a bit of gear.
Safety glasses, always important.
Yeah,
And safety gloves to avoid burning your hands on this very hot drum.
that's right. Now, you might want to... You want to put those on?
I will.
You might want to stand back a bit because it's a little bit dramatic what happens.
All right, let's do it.
Get that into there and get some cold water onto it. All right, so that water's turning back into water vapor.
Oh my god!
That's what you look like with 3,000 kilograms on your head, 10,000 kilograms on your whole body.
You know, I was expecting it to crumple like slowly over time. I wasn't expecting it to just go all in once.
Yeah, well, because it's circular, a little bit of it goes and the whole lot goes.
Wow.
They're quite strong for a while.
Yeah, that was awesome.
Yeah, you can hear the air is trying to get back in.
Ah. And now the pressure is equalized there. Inside
the pressure's now re-equalized, that's right.
Wow. That's one hell of an experiment.
Certainly is.
Looks like you wet yourself. That was so exciting.
That's partly true.
Oh, yes.
So when people go like deep sea diving and then they get like the bends and
Yeah.
like, their like body malforms, is there no way to correct that? Because they're
Well, so,
Hyperbaric, right?
It's gas which was dissolved.
yeah, it changes the biology of how your body works. There is a way that like, you're supposed to adjust more slowly so that you can compensate for that, but if you change pressures pretty quick, like the human body just really isn't good at dealing with those kinds of pressures. Like, why do we have spacesuits? It's not just so you won't suffocate.
yeah, it's no pressure.
Yeah, it's pressure. Like, you will actually just explode because there's pressure on the inside and there's no pressure on the outside. So the opposite of that would happen, where you would just like,
Combust.
yeah. So, yeah, that sucks. That's not a good way to die. Yeah.
So like in those movies where like they see somebody get like sucked out of a spaceship or something, really you wouldn't get sucked out, you just kind of explode.
Both things would happen. Yeah, you would get sucked out and explode. So you wouldn't see like
Which would happen first?
Wait,
though?
what did
This is actually a flaw in
So you don't
like.
turn into ice or
I thought people would
nothing.
freeze
Yeah,
into a
it's not
solid
like
thing.
this, that Star Wars movie where she's like, she's out in space and then she like uses.
has a force.
I mean, I guess like, she could have like a force spacesuit, but like, yeah, it's kind of bullshit. So, there's a lot of things that we get wrong in movies about space, like all the sound that you hear. We'll talk about sound in this class and how it travels through.
So we need to use space enough.
Now we know. Anyway, yeah, the physics in Star Wars is bad. Turns out George Lucas doesn't know shit about physics. There's a lot about cinematography.
They don't have like science
storytelling.
people on the scene like
So
helping
now
them.
they didn't. Now I believe the NSF has a call line at UCLA. If you're making a movie and you want a scientist, particularly physicists,
Yeah.
to fact check your movie, you can call the NSF and
That's cool.
Well,
your
that's
tax
what
dollars
they
at
did
work.
with-
Yes.
That's what they did with Endgame, that Avengers movie.
Oh yeah.
They
They
tried to do all the
fact
hypothetical
What
like
about
time
that
travel.
Interstellar?
Interstellar was like.
Interstellar is the
How
only one
accurate?
that's, well, the problem with Interstellar and the great thing about Interstellar is one of the producers is a theoretical physicist. So that helps a lot if you have one on staff.
The
Yeah.
Martian was also supposedly supposed to be pretty.
Yeah, the guy that read The Martian is just also, he's just a huge nerd. An amazing, if you've seen the movie's good, but if you read the book, he has all the calculations in the book, which like,
That's pretty intense.
and less Matt Damon. But you can imagine Matt Damon.
Maybe like 2 months.
Because he like calculates how many potatoes he can grow with his
It's like Goodwill Hunting the sequel.
and like how much water. He actually like does the calculation of how much water he can get from the hydrogen. Like yeah, like it's a pretty cool book, even if you just want to skim it. But yeah, it's very detailed. They left out a lot of the math in the movie
I'd imagine it's not as interesting.
for obvious
And
reasons.
they also have a runtime to fit it into.
Yeah. But anyway, so here's a clicker question. It's a fairly straightforward one, but we're gonna start the process of how we actually use clicker questions. So the way that we do clicker questions in this class is a two-part thing. So the first time you answer the question without discussing it, you discuss it in your own head. So just you and yourself, your inner voice, and whatever other voices are in there, and then we look at those results, and then you discuss with the people around you, and you try to decide if you're wrong or if they're wrong, and try to use like really incendiary language when you tell them that they're wrong. That is a joke. Be nice to the people around you, just to be clear.
There's still 2 more votes.
Really, D. All right. Well, we mostly think this was sealed in the mountains. Please discuss. Yay! Very seldom that we get 100%. So this is a water bottle that you take up to the mountains. You seal it in the mountains, and then you drive back to San Diego, which is primarily at sea level, and it looks like this.
Really?
Okay. Yeah, you can do this experiment yourself.
Okay, I'm gonna.
It's similar to an experiment you've probably done where you buy bags of chips and you drive into the mountains and they get real puffy. Or you take chips on an airplane.
I gotta see this.
Yeah, and so if you can get on an airplane, seal your water bottle, get off the airplane. It might not be quite this dramatic, but it'll
stabilize the pressure inside the cabin.
not
Yeah,
as
pressurized cabin.
the cabin is pressurized, but it's not the same pressure as sea level.
Cool.
So it'll be slightly different.
So
Mountains
if you
more
like
dramatic.
like here to Colorado, right? And then
That-
you get off the plane in Colorado.
Yeah.
Oh, yeah.
Then it'll be great.
These all good experiments. Yeah. Okay. But instead of just abstractly saying concepts about it, we're gonna put math back in. All right. Okay. So this is just a variation of pressure with depth. So this is a cup. It's filled with a fluid. Okay. It's a cylindrical cup, so it has a radius r. I'll say height h. Doesn't really matter. The gauge pressure is the pressure due to the depth you are beneath the fluid. So where do you think we should measure from?
From the top of the
From
water.
the surface of the fluid, okay? And if this is in air, you're measuring from the interface or from the top of the fluid you care about, okay? But it actually adds. So if there's a pressure, let's say you're in air at sea level. What's the pressure here?
Atmosphere.
Yeah, 1 atmosphere probably, or whatever that is in Pascals. 101.3 kilopascals, yeah. So that would be atmospheric pressure. Then you have to get the gauge pressure from the fluid. So you would start with whatever pressure is already here and then start going down, okay? So you'd start at atmospheric pressure and then it would increase as you go down in the fluid. So you want to measure from the top because, remember, as you go lower in a fluid, there's more weight on top of you, so the pressure gets bigger. So the gauge pressure, let's assume first, for now, this is in a vacuum, okay? If you want the pressure here, if we're in a vacuum, what's the pressure at the top? Zero, okay? Then you want the gauge pressure as you go down in depth. The gauge pressure has to do with the weight. What's weight? We just did this.
Mass times density.
mg, okay? So if it's not in terms of mass, we can make it density. So anytime you would think of mg, you could say it would be rho g. Okay, so anytime we're dealing with weight, you can expect to see rho instead of mass when we're talking about things like pressure. So this becomes rho. This is the density of what?
Of the fluid.
Of the fluid, okay? Of the fluid that's in the jar, so like the liquid in this case. G is just the acceleration due to gravity, 9.8 or 9.81 or 10, depending on how you're estimating that day. This is the gauge pressure, and this is D. What is D? It's the depth. The depth. So that it's the distance from the top of the fluid here to wherever you care about the pressure. Okay? So rho G D. That is your gauge pressure. Now, if you have another fluid on top of this fluid, you have to figure out what the pressure is at the interface before you can add to this to get the total pressure. But this is the general idea for any fluid. Okay? All right, so fluid density, depth. Hydrostatic pressure is just what I was saying. The pressure you start with plus the gauge pressure. Okay, so this is the total pressure at this point. So if you have an additional fluid, then you count that first and you add the gauge pressure from your other fluid. Okay, so in this case...
That P is the total pressure at the bottom?
So this P
Yeah.
is the total pressure at this depth.
Okay, sure.
In the previous slide, we were assuming there wasn't an additional fluid. So this would start at 0, and you just need the gauge pressure.
Cool.
Okay? Now you need whatever the pressure is you start with. It doesn't have to be atmospheric pressure. You could be on another planet. You could be high or low, whatever. You have whatever pressure it is from the fluid up here, and then you add the depth. Okay, so this is the pressure. In this case, this is atmospheric pressure, but it doesn't have to be. Okay, so if you have layers of fluid, you can figure this out too. You can just have a bunch of rho GDs that you add together.
Gotcha.
Okay, and this is the fluid density, this is the depth. All right. Hydrostatic. What do we mean by hydrostatic?
It's not moving fluid.
Not moving fluids. Guess what we call moving fluids? Hydrodynamics. Okay. It's just at least it makes sense. All right. So, hydrostatic pressure. Remember, you can use this when the fluid is not flowing. Once the fluid starts flowing, we have to use things like Bernoulli. Yes.
I'm just making sure I understood. I think I caught it what I was writing. If you had like oil and then water, two different fluids and then air, you would add them up. So if you have rho GD on each one of those.
Let's say there was another layer here, right? You would say atmospheric pressure plus rho GD to here.
Okay.
Okay. Whatever you have here, then you start measuring again from here in a different rho GD.
And so that would be a different
would
distance.
change.
That'd be a different depth, right?
Yeah.
Okay.
So if this were at like, let's say the distance from here to here is 10,
Okay.
you'd have like 4 and then 6.
I got it.
Right. Yeah. All right. So hydrostatic pressure. There's a fun fact. If you're along a horizontal line, pressure is always the same. If you have no fluid flow, okay? So pressure in a connected fluid is the same at any point along a horizontal line, okay? Doesn't matter what the shape of the container is. All that matters is the fluid is not moving, okay? So pressure is the same along a horizontal line, all right? This has some fun applications like hydraulics. Okay. So So here's a question.
Oh, here we go.
So first, answer quietly to yourselves. It's a time of quiet meditation. Or just
My internal dude.
okay. So please discuss. We'll vote again. Okay.
2 days in a row.
A is less pressure than all of these because these are all on the same horizontal line. Okay? And what do we call that?
All on the same line?
Hydrostatic.
Yeah, that's this rule of hydrostatic pressure. It doesn't actually happen. I guess it's just hydrostatic pressure. That's just what the deal with hydrostatic pressure. Yes.
I had a question about that question previously.
You have a question about the question. Okay. Which question? This question?
Yes, this one.
Okay.
I was thinking, like, shouldn't sea have more pressure because, like, looks there's more water above sea because, like, you look.
No, and that's because the force gets distributed pretty evenly. Otherwise, if it's not distributed evenly, let's say that would mean on each water particle you have unbalanced forces. Okay, if the forces aren't balanced, what happens?
They flow.
Yeah, you have acceleration, right? So hydrostatic means for each water molecule, the net force on the water molecule has to be 0, right? Otherwise, the water would be moving. So because of the fact that the water is not moving, everything along this line should have the same pressure. If it didn't, you would have flow. Okay, and that's also why this is only true, this horizontal line thing is only true for hydrostatic situations. If you have a hydrodynamic situation, that means you do have a force imbalance because water is flowing. Okay? Yes?
We are going over these fluid equations. Are we to assume that this is for all fluids, or is water just like super special?
Oh, all fluids.
Oh, okay.
Yeah. I mean, if this is, so like, name another fluid you would like.
Syrup.
Syrup. Maple or?
Oh my! Oh, you've done it.
No, actually, the answer is yes. Maple syrup? Yes. Corn syrup? Yes. Blood? Yes. Okay.
Oh my goodness.
Air? Yes. Okay.
What about things like glass that are actually liquid, but they're so solid? Glass is a liquid.
What did you say?
Mind blown.
Mind blown.
It's the second day.
Is it static though?
Well, it's always moving. It's always settling really low. But
I don't honestly. That's a good question. Glass is a little bit weird. I'm not sure from a physics perspective, it's considered a fluid in the same way that water is. But I think it is. It might just be like a special case,
right.
Because it's like part solid and part fluid because it does have some crystal structure issues.
Yes.
So which our definition of fluid does not have.
Right.
So I'd say that would be an asterisk fluid. It might be fluid more in the like definition of language, and also probably depending on what time scale you're talking about.
got it.
Yeah. No, I mean that's a good question. Okay. Here's another one. Using all of it. Okay, so we're mostly thinking B, but there's some A's and C's in there. Please discuss. We will. All right. The answer is B. Why is the answer B?
Because everything has to be equal.
And what is it equal to?
Oh, the hydrostatic.
Same height.
The line.
Well, what force is it in? What pressure should it be balanced with?
Air pressure.
Itself.
Atmospheric pressure, right? These are all open to the air. So if you pour it in slowly, you can consider that mostly hydrostatic, right? If you let it settle, okay? Because as you're pouring it in, it might not be even, but if you pour it in really slowly, it'll keep equalizing, okay? Because anytime it's open, that pressure has to equal atmospheric pressure because you're open to the air. And this is actually something that's true. That particular statement is actually true even in a hydrodynamic situation, okay? If you have water coming out of a hole in like a tank, all right, that water is coming out into the air. If you're at atmospheric pressure, if you're at sea level, then the pressure at that point where the water has left the tank should be equal to atmospheric pressure because there's a force balance. Now you'll notice that would mean the water isn't accelerating, right? It just has a speed. And that would mean you still have a force balance. Yes?
Okay, so if I have a pipe and the pipe has 3 holes in it, regardless of their linear, like 1, 2, 3, which hole it is, they'll all leak the same speed?
It's not that they'll all leak the same speed. The pressure at all of those points should be atmospheric pressure.
Okay.
So when we talk about the Bernoulli equation, there's other variables to consider, including speed, cross-sectional area, which is from the continuity equation, and height. So you won't necessarily have the same speed because that'll depend on the size of the hole and where it is relative to the other holes, but they will all have the same pressure.
All right.
Yeah. That's a very good answer. I'm proud of it. All right, measuring pressure. So for hydrostatics, any surface open to the air at sea level has this. What is this?
At 1 atmosphere.
1 atmosphere. This is atmospheric pressure. It just happens to be in pascals. And we like pascals in physics. I don't know why. I think because it goes nicely with the other SI units, but it's a lot harder to remember than 1. Surface covered by a gas, then your initial pressure is equal to the gas. Surface covered by another fluid, your initial pressure is equal to that fluid. Remember, pressure is defined as force over area. If you're at a depth beneath the fluid, the pressure you start with at the top of the fluid plus density of the fluid times G times the depth you are in the fluid, okay? Yes, pressure in a connected fluid is the same at any point along the horizontal line. This is all the stuff you need to know to do hydrostatics. Okay, so it's just my summary page. And now we're going to do an example.
Does it matter which gas? Any gas?
Any gas. Any gas.
There's no exceptions?
No, no exceptions. All gas. Okay.
Is that rho GD?
Rho, yes. It's squiggly P. Rho. Yeah. P, rho. P, rho. All right. Ready for an example?
Yeah.
Cool. There we go. Yes, examples. Okay.
Okay, so we're going to do an example. We have water filling the tube shown below. The taller part of the tube is open to the air at sea level, so we should know the pressure, okay? We want to know the pressure at the top of the closed tube, so right there. So we know from the whole hydrostatics thing that whatever the pressure is here should be the same as the pressure here, because if the water's not flowing, that means they're at the same height, okay? So, because of that, what we really need to do is find the pressure here. To do that, we have to start with the pressure here and then use our gauge pressure to add the pressure as we go down. Okay, so to do that, we start with this pressure equation, which is total pressure is equal to initial pressure from this fluid here, right, which in this case is air, plus rho g d for depth. And our depth here is going to be this. So our depth here, d, is going to be 100 centimeters, which is this here, minus 40 centimeters, which is this here, and that's going to give us 60 centimeters. We also know that P naught in this case is going to be 1 atmosphere because we are open to the air here. And since we're open to the air, we know, and we're at sea level, we know what the pressure is. It's atmospheric pressure. But of course, we want this in pascals, which is 101.3 times 10 to the third pascals, because that's the unit we like to use in physics. Okay? So now that we know that, we can plug that into our equation. So our total pressure is going to be 101.3 times 10 to the third pascals plus rho. Rho is going to be the density of water. And the density of water, just as a reminder, is 1,000 kilograms per meter cubed. So a nice, easy number to remember. So 1,000 kilograms per meter cubed. G is 9.8 meters per second squared, as it usually is. And our depth is 0.6 meters because it's 60 centimeters. So when you plug all that in, you end up with 107.2 times 10 to the third pascals, or 107.2 kilopascals. So remember, the key here is, first off, we have to assume we know the atmospheric pressure because we're open to the air, and then we use this line to find the hydrostatic pressure. So here we know, if we want to know the pressure here, we know we can find it anywhere along this line, and that's what we did.
All right, so I'm going to have you guys try a problem.
Okay, so this problem is a little bit of a variation from the previous example, but it's the same basic principle. We're still going to use this gauge pressure equation, which is pressure is equal to initial pressure plus this depth part, right? So that's all the fluid on top of you that creates pressure. So in this case, we see that we're still open to the air, but we're open to the air down here instead of right here. So that's a little bit different because remember, we're always going from the top to the bottom because this is depth. D is for depth, okay? So we want to figure out what the pressure is right here. So I want you to think about how this thing is actually made. This barometer is basically just a tube. You put the fluid in the tube, in this case mercury, which is, I don't recommend trying this at home. You really shouldn't have open mercury laying around, but this is actually a good way to make a barometer, and it's been done. So you take the mercury in the tube, and you basically put the bowl on top of the tube and then flip the whole thing over. So that means that there was nothing but fluid in the bottom of the tube. And what that means about this guy over here is that this is a vacuum. Okay? And what is the pressure in a vacuum? Well, pressure in a vacuum, that's going to be equal to 0 kilopascals, or pascals, right? So now we're starting from 0, which is a little bit different. Even though we know there's an atmospheric thing happening here, that's actually what we're trying to measure. So that's not going to help us at all, because you can see, if you think about atmospheric pressure, right? You know at sea level, in normal circumstances, it's 1 atmosphere, or 101.3 kilopascals, or 760 millimeters of mercury. Now you'll notice this is not 760. So do you think this is going to be more or less pressure than atmospheric pressure? Well, we can tell just because this is a smaller number, this is probably going to be less pressure. So we're going to expect a number that's smaller than 101.3 kilopascals. And so let's start by actually trying to do this. So this is going to be our P naught now. Okay, because we start from a vacuum. And then we're going to go down from here to here, this H, that's 750 millimeters. Okay, so now we're just plugging stuff in. So P is equal to P naught, which is 0, we'll call that pascals, plus this density of mercury. Now you'll notice this is in grams. We're going to need this to be in kilograms in order to get the right units. So how many grams are in a kilogram? Well, that's 1,000. But the other tricky thing is this is in centimeters cubed, so you have to convert from centimeters cubed to meters cubed. Okay? So if you have 13.5 grams per centimeter cubed, you actually have to do the conversion. So that's going to be 1 kilogram is equal to 1,000 grams. And then you have, remember, a centimeter cubed, right? 1 centimeter cubed is equal to 1 times 10 to the negative 6 meter cubed. Okay, so when you do all this, you end up with 13,500 kilograms per meter cubed. So 13,500 kilograms per meter cubed. Once again, G is 9.8 meters per second squared. And then your distance, which is 750 millimeters, or 0.75 meters. Plug all this stuff in, and you get 99.2 times 10 to the third pascals, or 99.2 kilopascals. Now remember, we were expecting this to be a lower pressure than atmospheric pressure. So is this a lower pressure than our atmospheric pressure in kilopascals? Absolutely. This is smaller than 101.3. So that means we probably did this correctly. We've checked our answer, and we're done.
Yeah, I mean, don't eat. You guys haven't promised not to eat the mercury.
Did you eat it or drink it?
Well, drink, yeah. Just don't ingest the mercury. Okay? It's really a semantics thing. So we talked about how pressure is all the same along a horizontal line. Another thing that comes from something called Pascal's Principle, since we're already talking about Pythagoras, another P guy, okay? Pascal's Principle. Try to say that 5 times fast. Any change in pressure at one point in the liquid is transmitted to all points in the liquid instantly and equally. Now, obviously, this is kind of a model, because I'm sure if you could get like a high enough speed camera, that's not totally true. But effectively, in the time scale that we live in, this is a very, very good approximation, okay? So, anybody think of any applications of this?
Radium. Car jacks.
Yeah, car jacks, okay? So this is how car jacks work. Hydraulics or whatever. It's a hydraulic lift, okay? So here's a car. I believe that's a Volkswagen Golf. Here's a fluid of density row. So if you press down on here, okay, that's going to raise the car, okay? Now, what do we know about this line? Same pressure, okay? So if you, and remember, what's pressure made up of?
Force over area.
Force over area, okay? So what we've done is we've displaced this a little bit, and that gives that, we start with a force 1 and an area 1. Okay, what do you notice about this area versus this area?
Smaller.
This area is much smaller. So if we apply a small force over a small area, what happens over here?
Good to have. Big force.
Big force, but over a
Big area.
big area. So pressure is the same, but we can use a small force to lift something with a lot of weight.
It's amazing.
Okay? Yeah, it's like, it would be magic, except it's
Science.
okay? So, yeah, you can use this large displacement to get a smaller displacement, okay, of something very heavy. Okay, think with a large, wait, what?
It's a witch.
I knew it was going to happen sooner or later. It's been a good run. How do you know she's a witch? She looks like one. Okay. All right. So let's try this out. Okay. We're not sure. You went a minute and a half.
There's no time like that.
I can't go back.
All right, let's see how it is.
There goes.
I'll just email me. Actually, it's. Do you guys want the secret?
Yes. Pretty much know it.
It's 50%. Yeah, you just have to. You really have to only do 50%. So just don't like leave now, and then you'll be fine. Okay. You guys mostly think me. Oh, okay. So what's the force here?
600.
Well, that's the mass, right? 600 times
6,000. Gravity.
So it's like about 6,000 newtons.
6,000.
Okay, 6,000 newtons over this area.
Okay.
Yeah.
Okay, this is 10,000 newtons over the same area. So obviously this is going to need more force because you have more force on this side with the same area. Okay, but what about over here? So this is 600 over this area. And then you double this, right? So you have 6,000 newtons. But you also double the area. So the pressure is the same. So the force you apply over here is the same. Okay? So that's what's so powerful about a hydraulic lift. Okay? If you want to lift more force, you just need more surface area. Okay? Because it's a pressure balance, not a force balance. What you're doing is redistributing the work into the fluid.
Good job.
Thank you. Yes.
Just to get a conceptual, if it was lifting one car up and you use like a ton of force, right? It would just lift up one car. But if I had several cars on several lifts connected to the same thing, it would still be 1 ton lifting them all at the same time.
So wait, I'm sorry. You have to re-explain the question.
Okay. Like for example, in the example C, it's 2 vehicles instead of using 600 pounds, or 3 vehicles or whatever. If it's the same lift and the same pressure, it could lift all of them up equally at the same time, and or just one if you're choosing to do one.
Yeah.
Science, change or
I know, right?
That's not what the question's asking. But, I believe.
Just think about it with the open one.
Yeah, you just need more fluid.
Well, if you want the same speed, would it take a lot more force?
Right.
I think it will, like in this case, you can see there's a lot more fluid. You might not. I have to check on this, but I think the height changes are a little bit different. Like you won't get as much height differential. So I'd have to double check on that. Yes.
If the area under 1000 was proportional to the other ones, would A be true? If the area was
So if like this area got big, a little bit bigger?
Yes.
Okay.
Or if they were all 600.
If all of these were 600, then A would be true, but this is 1,000. Yeah. When A would be 600 does not equal 1,000.
What's the situation with the distance displacement?
I'm pretty sure that it does affect displacement.
Right.
That's what I said, yeah. I just need to it's hard for me sometimes to remember these things on the spot, but I'll check on it. But I think the I think the difference between here and here, the forces needed are the same, but the distance displacement will be
It would move less on C, I would think.
But I will double check on that, or you can. Yes.
So because the distance displacement's the same, so if you had a car jack, it would be the same amount of force, it would just be more pumps or...
Yes.
The force needed would be the same, it would just be more...
I'm not, more pumps?
Yeah, because you have a car jack, you pump it up.
Oh.
It would just be more pumps.
Are you talking about a hydraulic jack?
Yeah.
Or, okay. I'm not as familiar with how those work in the day-to-day. I'm more of a theoretical car jack person. I have to look that up on howstuffworks.com. As far as I understand, with cars, you take them to Toyota, and if it's not like a fuse or like a light bulb, I don't usually fix it.
That's fair.
Because I paid for the extended warranty.
That's fair.
Yes.
So, I know we mentioned it 2 slides back, but does not the viscosity, the density of the fluid affect how efficiently it can transfer? Because the fluid's incompressible. So why would you choose jack oil, which
you don't want to use air, which is a fluid, right? You need an incompressible fluid.
Yeah.
It has to be done and slow enough that this works, right? Yeah. So different fluids would have slightly different effects. You could get this effect with all fluids. It just, from a practical perspective, some are going to be better than others. Yeah. And that is what we call engineering. And you can harass your engineering professors about that.
Wasn't it because of the viscosity?
Yeah, the viscosity will have, because, honestly, this is the beginning. So we're talking about ideal fluids, which are don't have this crazy, obviously using maple syrup might not be the best choice for this, okay? Partly just because it's gonna crystallize and there's gonna be sugar everywhere and it'll be delicious when it all falls apart. But there are other factors to consider. But hypothetically, you could make a hydraulic lift with maple syrup. I don't know why you would.
Final project.
Just because you can.